Welcome to Study Loop.
Here we're given again a package sliding on a track, and it's being slid with the velocity this way, and it goes around an arch here, a semicircle, and gets deposited up here on a track that's at a higher level. So again, we need to figure out what kind of velocity we need to be giving the package down here so that it can make it all the way up here. And in the first case, this upper track doesn't extend around, so we need to make sure that the normal force on the package is always in the negative radial direction. So it's always pushing back on the package because there's nothing over on this side to keep it from to support it. In the second case, we just need to make sure that the normal force in this region is in the negative radial direction, and also we need to make sure in both cases that we have enough kinetic energy down here to get the package up here with some non-zero kinetic energy. So we have these constraints, and if we look at just conservation of energy for an arbitrary position of this package. The potential energy is 1/2 mv squared. The kinetic energy is mgr1 plus sine theta, and I've measured theta being positive from the positive x-axis. So we're worried about theta going from pi over 2 to 3 pi over 2. And then that equals the initial kinetic energy that we give the package down here. So we can solve for what the velocity is at any point on this track. And then we know the acceleration is minus v squared over r in the radial direction. So the radial direction is pointing this way. And the radial unit vector is just cosine theta in the x direction, sine theta in the y direction. We're going to say that the normal vector is in the radial direction. Okay. And we're going to need that to be negative for the package to not come off the track. Then we have the weight of the package that acts in the vertical direction. So we do a free body diagram on the package, and we have the mass times its acceleration, and the two forces that we have are the normal force from the track and its weight. And I'm going to take the dot product of this, or project this vector equation in the radial direction. So I'll take the dot product with the radial vector. That means that this term just becomes minus mv squared over r. This term just becomes n, and this term here is minus w sine theta, because er, we need the j component, or the j component of the er vector, which is this. And this gives us an equation for n in terms of the weight, the angle, and v squared. And we need, in the first case, that to be negative. So we can solve for n, and what we're going to do is we realize that the minimum value for n is going to occur when theta equals pi over 2. So when the package is at point C. So we plug in theta equals pi over 2. And then set this to 0, so that we can find the limiting case. We find that v naught needs to be greater than square root of 5 gr. So that's we need that depends on the gravity and the radius of this track, mostly because the radius of the track depends on how defines how high how much extra gravitational potential must be given to the package, or the package will have after it gets up to the top. We can then solve, if we know this, then we can figure out what the normal force at point B is, or the velocity at point B, and so that is at least 3g square root of 3gr. And then the normal force at point B is when theta equals pi. And so we can put pi in here, and we can then we know theta naught, and we get that the normal force turns out to be 3 times the weight. Again, we're not given any values in this problem, so we're just doing everything symbolically. So the normal force is at least 3 times the weight of the package at point B. And we can also see that at point C, the velocity is g times r, and that is indeed greater than 0. So we'll actually make it up to the top of the track with a non-zero velocity. Now, in the second case, we have part of the track down here to support the upper track to support the package. So we need to make sure that BC is greater than 0. And to make sure that happens, we need to figure out using conservation of energy that V naught needs to be greater than square root of 4 GR. And then the normal force at point B is going to be at least twice the weight of the package. And we can see that it makes some sense, because now that we have some extra support here, we don't need to get the package going as fast so that it keeps contact with the outer edge of this loop. So it can then, as it gets up here and slows down, the lower track can support it then. So it makes sense that this is less than this, and obviously then that this is less than this. And then we can figure out what the normal force is if we plug in our V naught here, and we get this expression for the normal force, or it's the weight times 3 sine theta minus 2. And what we're worried about is the normal force from pi, from point B to point A, so from pi to 3 pi over 2. And we can see that if we plug those values in, that indeed this thing is negative, so that we aren't going to fall off the track as it's rising up from the bottom up to the point here, which we would expect, but it's good to check.